Cool. Okay then, so it's nice to see everyone, and it's a real pleasure we're going to hear from Mike Durand and Chris Derksen today. So Mike's going to be discussing some of the main messages of a recent review paper, so global monitoring of SWE using a high-frequency radar. That is also going to be linked to quite a lot of what Chris is going to be talking about the terrestrial snow mass mission, which is a kind of a community initiative, particularly based in Canada, and it's hoping to start to try and address in a more sort of a practical sense some of the things outlined that in the paper that Mike is going to speak on. I won't talk any more about that other than to say, ask the presenters, we've got about roughly 30 minutes each with 10 minutes questions, and the two should hopefully run seamlessly together. So I'll stop speaking now, and if Mike, I'd be very grateful to you to take it away. Thank you.
Yeah, will do. And I'm really excited to be talking about this. Do you think you could make it so I can share my screen?
Let me know if
yeah, it says host disabled participant screen sharing.
Okay. And let me make you co-host right here.
My apologies. I should have tried that earlier. Thank you.
It's okay.
All right. So yeah, this is really a story about a community effort to create this paper that's just come out. I'm Mike Durand. I'm at Ohio State, but and I was the second author. I helped coordinate the effort, but it really was a group effort. I just want to make sure to acknowledge that carefully. We had 28 different authors. Affiliations spanned quite a few countries. The topic is using radar to measure snow water equivalent at the global scale, something that a number of satellite proposals in the past and current ones going on now have attempted to do. I think we would all agree that this would be game changing. When that satellite's up there and producing accurate snow water equivalent estimates globally. And so the question is, how much progress have we made towards that lofty goal? So we ended up with a pretty large manuscript. It's kind of a monster, 30,000 words, more than 200 references. And what Nick suggested I talk about is not just like the technical message of the paper, but also try to tell the story of how the paper came about and kind of where it came from. And Nick and many others, Chris and many others were involved throughout that process. So I think it's a story worth sharing. So I'm excited to talk through that. So it was a lengthy process. I think the idea for it came when someone asked a question, you know, has there been any progress in this space recently? And I kind of immediately, I was in a group meeting and immediately said, yes, there's been tons. And then realized that there was no like easy way to where that was all summarized. So we started discussing in August of 2020. It was published exactly 2 years later, just about 2 years later. And it was kind of this group effort throughout, as I'll talk about later. But we submitted it about exactly halfway through that period. So it didn't go quickly. The way it kind of came about from my perspective anyway, I'm very, please interrupt and set me straight if you were there and wanted to set any of these things straight. This is all how I kind of remember it, but there was this working group, which is kind of on hiatus at the moment, came out of some of the SnowX community, and the topic was on microwave scattering approaches for measuring snow water equivalent, which falls in this overall space of using high frequency radars to measure SWE. And that working group had some people that were funded under SNOX, NASA terrestrial hydrology program, but a lot of additional folks from around the world, including many of the co-authors and folks on this call now. So we had bi-weekly calls throughout this process, kind of over 2 years, with many kind of gaps, and of course, as working groups do. But generally, every couple of weeks, we get on and talk. So we talk both about things on this review paper and also topics just to the working group. We did notes after each call, try to keep everyone looped into what was going on. And then we kind of did everything in a giant Google Doc, starting with an outline and then breaking up into teams with writing assignments for the kind of first phase of writing. I think some of the interesting, pieces of the process was, as we sort of struggled with what kind of paper we would write. I was thinking back about this, and for a while we really agonized about the journal, which I'll talk about here in a second. And we had originally been targeting something like reviews of geophysics, or rather, there's only one reviews of geophysics. We were originally targeting reviews of geophysics, and I was using this model of the paper that Doug Alsdorf wrote, along with co-authors, to kind of lay the foundation for why we needed the surface water and ocean topography mission, which is actually scheduled to launch here in a few weeks. Very exciting. So 15 years ago, he wrote this paper, and it's a beast, but it really looks comprehensively at measuring surface water from space, as the title replies, and it reviews everything that space. Incidentally, it's been cited a ton, and it was really helpful. That was kind of one direction we could have gone, and instead we eventually pivoted and said, look, we're really interested in writing a technical approach, starting as our starting point being this particular method and this particular approach, X and KU, snow water equivalent measurements, rather than a true comprehensive remote sensing of SWE review, which others have done. I'm not sure if that's making sense or connecting, but it was an important scoping decision for us. We spent a long time figuring out journals. So we actually contacted reviews of geophysics. We kept pushing this idea. We wanted to review this particular space, and they're like, this seems too narrow for reviews of geophysics, is what our impressions, reading between the lines of input from their editorial folks. So that when we got that negative feedback from them, it helped us kind of rescope and say, look, we were really interested in, as I mentioned, capturing the latest developments in KU remote sensing of SWE, which I found in some of the minutes I'd made years ago. So we chose these 3 journals, and we ran into another interesting thing where, we'd get on these Zoom calls, but it wasn't obvious that we were coming to consensus on which journal we preferred. So we created a survey and ranked them using this little 5-star system for which journals we preferred. And I think the important thing about that is it really gave everyone in the process kind of like an equal voice, right? One person, one vote, one chance to review each journal, which kind of helped build, I thought anyway, further consensus with the process. So in the end, we preferred the cryosphere to IEEE TGARs and JSTARS. The outline we came up with, I'm gonna maybe cut this a little short. The outline we came up with is really focused on this technology rather than other ways we thought of telling the story. So we really talked about, there's a real brief introduction, and then Chris wrote this really nice section, Chris and others on edited and others on, you know, the scientific objectives, the point of all this. We have a long section on, you know, kind of the forward problem, right? So how radar interacts with snow-covered landscapes. Then we talked about retrieval algorithms and their current status, like how do we, you know, infer things about snow using radar. We ended up with a really large section on synergies. So how, you know, building on the idea that there's probably not ever going to be a one-size-fits-all technology that measures every kind of snow for every application, right? So we spent a lot of time on the synergy section, and then again, Chris wrote a section that was essentially a kind of a status on TSMM, which he'll update for us some months or year plus after this section was originally written. I don't want to talk through all of this in great interactions, but I think it was helpful to kind of realize that, like, no matter that there was just a lot to talk about. So there's like the classic thing you might think of how radar interacts with snowpack, but there's also how radar interacts with the ground beneath the surface. There's been a lot of advances there. There's a lot of advances on how radar interacts with forest vegetation. We had this interesting section where we just focused on what a lot of us felt like were some of the biggest advances, which were that there's been a lot more measurements made. There's a lot more focus on in situ measurements and airborne measurements in the past 10 years or so. And then we had this nice section on spatial scale and how spatial, you know, advances in spatial scale help us link all of these different pieces from in situ to airborne to spaceborne. Let's skip. So a few of the like main, you know, talking point sentences from the abstract, I think help set the overall tone for what we found. So, you know, physical basis of this is all based on our understanding of volume scattering by millimeter scale snow grains. The inference requires an interdisciplinary approach. In order to estimate snow water equivalent, these kind of measurements, you need to understand a lot about priors, about spatial scale, as well as electromagnetic theory. And then there's a lot of advances that have been made in field protocols and in techniques to measure things on the ground that help us to better constrain our retrievals. I wrote down 2 slides of sort of granular advances in each of these different areas. I don't think I want to read them to you in part because I'm just going to start coughing. But it helps when you see the scope of what this problem involves to realize that progress is not like this single retrieval algorithm, but rather, you know, how many both 3, 5, 10 different pieces that together all come together to better understand these things, from forward simulation improvements in how we deal with the priors and the retrieval algorithms, to the ground and the vegetation, to spatial scale. And all of that together is this interdisciplinary advance in this field. Our review process was great. We got a signed review, and of course in the cryosphere, this is a discussion that is public. Go read it. But he, Professor Helmut Roth, did an amazing amount of work on his review. He was the PI of the Core H2 of the European Space Agency proposal of a technology just like the one we're reviewing 10, 15 years ago now. And very thoughtful, very thorough. Our response document was about the length of a normal paper and greatly improved the manuscript. I was going to scroll through the paper and talk through some of the different pieces, I think my voice is almost dead. So I'm just going to stop here, and maybe Chris can have a little additional time, but please check it out. It was a major effort, took a long time, and I think it stands as a nice community driven consensus, model process to create a snapshot of where we were at kind of a year plus ago on this topic. Of course, it's already out of date. There's a lot of exciting things that have happened, near the end of that we didn't squeeze into the paper. The process had bumps. There were challenges. I'm not talking about those necessarily, but suffice to say, there were getting that many people to all work together was not without challenges. But I think that by trying to, go with consensus and a slow and thoughtful process, we ended up with a well-considered and comprehensive paper. So, and we hope that there's a big improvement here, a big help to future satellite missions, things that are in the proposal and development process. I'm really excited to hear the latest about TSMM. There's also an ongoing NASA Explorer proposal led by Ana Barros and others that's also building on this technology. All right, so I was going to talk a little longer, but I'll just stop there. If it's okay, Nick, and turn it over to Chris.
That's absolutely fine. Are you in fit state to take any questions right now, Mike?
Sure, I can always answer in chat if I can't talk.
Okay, right. I mean, please do say no if it's just too much. We are going to have some time, so if you are able to do that. Clearly, the paper's been out a while now. People might have some questions about the science within there, or any of the elements of what Mike's talked about, which was the process behind it, the community building process behind it. Maybe before Chris starts off, does anyone have any kind of immediate questions? I'll try and look in the chat at the same time. If you do, please just unmute yourself and speak. I've got one, Mike, while you're having a little drink of water, and that's purely about where you think this has got us as a community in terms of how this could be leveraged for future work, because you started off by saying we've done an awful lot, but it hasn't been written down as a coherent kind of document. What do you think have been, as a consequence of this, the advantages for the community in having a paper such as this? Because it was no small undertaking. This was a non-trivial task, as you've very well outlined. What do you think are kind of the payoffs for the wider group now?
Yeah, I gotta say, I'll be completely honest. I've struggled a little bit with that question, and I thought about how to answer it, and I thought about trying to tie something together in a coherent and grandiose statement. And I think that I'm going to stick with the idea that a lot of people were involved with this and aware of it, and even Professor Rutt, listening to his critiques and skepticism and answering those, I think creates a broader base of understanding of where this technology is at across future potential reviewers of these proposals. I think the ultimate answer to what you're asking, we'll see how the current mission proposals and missions in development fare in their next processes of review, right? So I'm sorry to be vague, but that's where I'm at with it.
As part of the community to help with that, I think one of the things I found most enlightening was what mattered to some people and what didn't matter, because the initial draft was a lot longer than what has gone in, and so we were cutting and cutting and cutting, and what people felt could be lost and what other people felt were essential to have in were very different. And it was interesting to hear and see those kind of opinions from a broader bit of the community. You rarely get that opportunity to see. Not looking for consensus, but we're looking for acceptance, I think, of a broader perspective. Does anyone else have any questions right now for Mike? Either please stick them in the chat or just unmute yourself
I have a question, Mike. Really awesome work with that. I've read it and tried to read certain sections, but it's very dense and very technical, which is great. I have a question on just there's a lot of in this sequence of papers, there's a lot of different method, or it's a similar method of this retrieval, but it's like slight perturbations, slight differences that people use and all, whether it's from ground-based, from airborne. And just like as this approaches forward towards a satellite proposal, how is that decision being made on like what's the right one to be using, or using different retrieval methods in different areas? And how is that going to be decided as like within the proposal, or is it something where certain retrieval methods work better in different areas and that just has to be pinned down, or it's just broadly the implementation on a global scale with all the different methods and different groups who use slightly different methods?
Yeah, it's a great question. And I'm not sure I've got the perfect answer. I would say that what I found was that there was probably about 5 or 6 different papers, different groups that have written down an algorithm. They're almost all identical. They're very similar. I think what's different about them is whether they include snow water equivalent as a prior. So it's like, do you start with some guess at what the SWE is or not? That's almost philosophical. I think that some folks have shown good results without having any prior at all. One interesting innovation that we highlighted actually in our response to Professor Rott's review was this idea that if you change the problem on the prior of grain size from just needing to know grain size to some percent to classifying it into like these 2 different regimes of higher versus lower backscatter, you actually change the feasibility of the inversion problem. So I think that's interesting. But I think ultimately that's where the literature is at in terms of how this gets worked out in missions. I'm really excited to hear what Chris is going to say. There's a lot of development with the Explorer proposal. These missions are like these little, pressure cookers where you gotta like take the pieces that are around and assemble them in the best way you can to show that you're going to, deliver scientifically relevant data products, right? So there's a lot there. So maybe stay tuned on what's going on with missions.
Cool. Thank you.
Great question. Thank you. Okay, so Mike's trailed Chris enough times now to suggest that we should hear from Chris. Yeah.
Okay.
The link, to the paper has just been put into the chat by Ernesto. So thank you. Well, let's hear from Chris now, and certainly I think after that there'll be scope for having questions about both because they're tied together. That was the purpose of linking these two within this seminar. So Chris, could you take the floor?
Yeah, for sure. Yeah, can you hear me? Is my
Thank you.
audio okay? Yeah, you can hear me?
Yeah,
Good.
thank you.
Yeah, thanks, Mike, and thanks for powering through. Clearly, you're not at the top of your game today, but impressive endurance to get through that. And you really led in very well to my presentation today. And I really think you're kind of underselling the significance that review paper has for an activity like development of the terrestrial snowmass mission. I mean, it puts a lot of science in one place, which is great. And maybe most importantly, it shows at least the Canadian Space Agency that the international snow community cared enough to put the time and effort into this collectively, and the number of names, the number of countries of people who joined in and helped the effort just shows that there is community buy-in, and that carries a value that's hard to quantify. So really, it's really an important piece of work from the community. So yeah, I'll give an update today on the terrestrial snowmass mission, and I'm going to draw on some of the themes that Mike talked about. I'm going to provide sort of 3 things, I hope. One is just an update on how we're positioning the mission in what remains a competitive landscape in Canada. So and to be clear off the top, we are not a fully funded mission at this point. There is funding, there is money being spent on development of the mission, but we've not yet been selected for implementation of the complete mission. So that challenge remains ahead, but we're still in the game. I'll give you a quick update on the mission activities, kind of where we are, and then most importantly, an overview of the mission analysis approach, which kind of builds on the question that Jack asked, how we're approaching this. I'm not going to give a lot of specifics out today, but from a high level I hope I can show how the international snow community, the contributions people have made, both formally and informally, have really advanced the concept forward for us. So I'm giving this presentation on behalf of the sort of small TSMM science team at Environment and Climate Change Canada, as well as our partners at the Canadian Space Agency who are working with us, as well as industry partners as well. So let me just see if I can advance my slides, which I don't seem to be able to do. Oh, there we go. So I just thought, from the positioning of the mission point of view, the USGS released fairly recently this awesome new graphic of the water cycle, and my intent here is just simply to show through the red boxes that nearly all components of the terrestrial water cycle have had or will have dedicated satellite missions to those components. So whether it's GRACE and GRACE follow-on, what they've done for groundwater, SMOS and SMAP for soil moisture. We have SWAT coming up, which is super exciting for rivers and lakes. GPM, of course, for precipitation. On the cryosphere side, we have ISAT-2 and Cryosat-2, but we've never had a dedicated mission for seasonal snow on land. So it's forced us to extract the most information we can from other missions, which we've done to varying levels of success, I think. But TSMM is one opportunity, and I want to emphasize that careful choice of wording. It's one opportunity to address a key water cycle observing gap that really is critical for northern countries like Canada, and that's why CSA is investing in this effort. There's a lot of text on this screen. I'm not going to go through all of it. I'll talk a little bit about the specifics of the mission for those who aren't familiar with it. It's essentially a 500-meter grid spacing KU band radar at 2 frequencies, so the KU low and KU upper. We use 2 frequencies to help address some of the uncertainties related to the influence of snow microstructure. The driving factor behind the design of the instrument was to cover all Northern Hemisphere snow-covered areas about every week. So that means we have to have a wide swath. We have to have a resolution compromise to achieve that wide swath. So that's where we're at 500 meters. I think everyone on this call understands the mission drivers, why snow is important. So I won't talk too much about that. But there's a couple of things in the bottom box here that's really pushed interest in the mission forward over the past couple of years. One is related to flooding. So stream flow prediction in Canada remains an important activity. The federal government spends a lot of money on disaster relief related to overland floods, about $2.5 billion in the last 5 years or so, or in the 5 years captured by the 2016 to 2020 time period. So there's definitely a prediction component here. We also know from a sort of freshwater supply point of view that in Western Canada, I know this is the same for parts of the US and most of Europe, our freshwater supply from glaciers is finite. That resource will be gone by the end of the century, for sure. We know this now, and this increases pressure on how we manage the freshwater resource we get from seasonal snow. On the science side, we have made recent advances in land surface modeling and understanding KU band radar response to snow, and that's exactly the piece that's captured in the review paper that Leung and Mike led. And then finally, on the industry side, Canadian industry has a lot of capacity and expertise on radar through the RadarSat program, typically focused at C-band, obviously, but there's a lot of interest on the industry side to do something different, to develop a higher frequency KU band mission. And cost, of course, is always a factor. So we're looking here at a low cost, lower mass spaceborne radar system. This is the technical concept. I won't go into too many details. I've presented this many times before in many different venues. So I won't go into the details on the radar performance. Suffice it to say that we've scoped this out as a Pathfinder mission. So that means we have provided industry with a specific cost cap, with a specific set of science requirements, and said, please design us a mission that for this cost value can meet these science needs. And they've been wonderful in achieving that goal. So what we have then is this wide swath. So it's about a 250 kilometer wide swath, 500 meter grid spacing. The map on the top right here shows for North America what the standard imaging, the nominal resolution swath looks like. And then for a few watersheds, we've just overlaid what the 50 meter strip map mode looks like. So we did want to include a higher resolution imaging mode. For certain regions and certain times of year, we might want to use that. Of course, we lose coverage then. So that's what the narrower swaths indicate here. We're planning on acquiring data over the mask shown, the Northern Hemisphere winter mask shown here on the bottom. And we will acquire data over the Southern Hemisphere as well. This is not just a Northern Hemisphere mission. And I will say that I think we maybe need to do a bit of work in refining the mask over the Andes, for instance. But we do want to keep this global perspective in mind. It's a Canadian-led mission, but it's not Canadian-focused from a data point of view. To achieve coverage of this sort of mask, we need to have the SAR on a lot, which is a bit tricky for the engineers. So we need to have the SAR on about 25% of each orbit. That's a fairly high duty cycle. So they've had to do quite a bit of work to design mass power and heat dissipation budgets that can meet that need. But we think we're there at this point. And we want to have the mission last for at least 3 winter seasons. It will have fuel and other things on board to last a lot longer. And of course, the hope is to get many more years in that. But the minimal design life for the mission is 3 years. The science drivers, as we pitched this in Canada, are very simple. The overarching science questions at the bottom of this very simple flowchart are very straightforward. We simply want to address, in general, 2 basic questions. How much water is stored as seasonal snow? We have a really hard time answering that question for a country like Canada. How is it varying in space and time? So that kind of addresses the climate services question. And then on our operational environmental prediction side, we want to be able to predict and understand the contribution of snow to the water cycle, and through hopefully intelligent use of data from the mission improve our streamflow prediction, including flood forecasting capabilities. So the overarching goal, of course, is that if we have enhanced snow mass information, or the overarching context is if we have enhanced snow mass information, we will be able to better safeguard water and food security, support economic activities, ensure ecosystem sustainability, and protect from flood and drought risks. So those application areas, are really the key drivers. It's a very applied sort of mission. I don't have my chat box open on my computer at the moment. So if anybody has anything that needs to be answered immediately, just intervene or Nick chime in. Otherwise, I'll wait for questions at the end. The mission status, where do things stand? So the long story going back was that there was what was called a pre-phase 0 industrial study completed in 2018. From that, a phase 0 industrial study was completed that focused on one of the concepts that was identified from the broader survey of potential concepts that was done as part of the pre-phase 0 work. That wrapped up in September of 2020, phase 0 did. And for those of us familiar with the sort of phasing step, it goes from phase 0 to phase A. That's the next step in the mission development process. We're currently in what CSA calls a mission planning phase between phase 0 and phase A. What's a bit unusual about mission selection at CSA is that once you are selected for phase A, so to get into phase A, you've effectively been selected for full implementation of the mission. At most agencies, including ESA, you go through phase A and then the mission selection process occurs. So I guess the good news is it kind of shifts the time horizon forward and the number of steps forward. So we actually only have one more approval process to go through, but it does then shift some of the things that you would typically do in phase A into phase 0. And so answering Jack's question specifically, how do you build a retrieval system that works in multiple regions? That typically would be a phase A type question. If we can't answer that in this current planning phase, though, we're going to have issues getting into phase A. So it's just it's a bit of a delicate balance, a tightrope that we're trying to walk at the moment. We have 3 major themes of work that's ongoing at the moment. The first is advancing the technical or technological readiness for the mission. That occurs through the CSA Space Technology Development Program. So through a project that was finished last year, an industrial contractor actually fabricated a subarray. It's currently in Finland. Our collaborators at the Finnish Meteorological Institute have the subarray mounted on their tower. They've successfully been able to interleave their radar electronics from their existing radar on the tower to do experiments with the subarray. So that work's ongoing. And it's kind of cool just to have something that was essentially a 3D printed subarray now collecting real data in the field. So thanks to our Finnish colleagues for that. What's coming up soon, which will be exciting as well, is that CSA is initiating investment in the radar transmit receive module development. So the goal will be to increase the TRL on that a couple of steps. And that contract will be put out, or the bids will be accepted in the next few months. So that will happen in the next year or so. On the programmatic positioning side, that's kind of a vague term, but it's what I like to use to describe all the work you do behind the scenes to make people care about your mission and help sell it. So 3 major things we're doing there. We just completed through a consulting firm a socioeconomic benefit study that was very helpful in quantifying some of the benefits of a mission like this. We have a document called the business case. This is what we use to sell CSA on the economic value of the mission. I think a mission like this sells itself in the sense that, the costs of damages from floods in Canada that are driven by snowmelt every year greatly exceed the cost of this mission. The value of the fresh water we get from snowmelt every year vastly exceeds by many orders of magnitude the cost of this mission. So that's kind of the approach that we take in preparing the business case. We have to prepare a few less interesting documents as well, the user requirements and mission requirements documents. These are a bit more technical. They're in the final stages of preparation. And then another really key part of the programmatic positioning is partner engagement. And I'll talk a little bit more about that later and some of the opportunities that we may see developing there. And these partnerships include formal agreements, perhaps with other governments, international partners, and then just the myriad informal scientific collaborations and partnerships that I'll get to that have really advanced our readiness for the mission. That leads to the fourth area here, that our bullet number 4 on this slide, which is the advancement of science readiness for the mission. We have actually Richard Kelly is sending me Slack messages right now. He's in the air over a field site near North Bay, Ontario, collecting airborne KU band data with his instrument. So we have a campaign that will run during this winter where we'll be flying Richard's radar every 2 weeks or so from now until March, or end of March. And that will feed into sort of a retrieval test bed experiment that I'll talk a little bit more about later as well. The really exciting piece is that next week we have the kickoff meeting for the mission simulator contract. So we have an industrial consortium that will be preparing a mission simulator. That means we'll basically have synthetic KU band radar data that will be produced from the simulator. The simulator will be fed information from the operational environmental prediction system at Environment Canada to help generate that. There's a radar geometry module, radar performance module. So it really allows us to do, I hope, many really interesting experiments on both producing and using synthetic KU band radar data. That simulator is not a trivial thing to build, and so we won't have that ready for about another year, I would say. And so we're ready, but our goal is also to make that open source. So we hope that that will be something useful for the community to benefit from widely as well. A final point to make is that there will be many months of the year when the tasking demands on the satellite for snow are minimal. And so we think there's some exciting capacity here to address additional application areas. We've never had a KU band SAR in space before. We've had a scatterometer, not a SAR. I think there's things we haven't thought of yet that other people probably have thought of. It would be interesting use of KU band radar data. So we're hopeful of some new opportunities that will develop there as well. I'm not going to spend much time on this. This is just the timeline. So we're in this green box, the pre-formulation phase. Sometime in the next couple of years, we will cross the hurdle into the next phase. The timing of this is a bit up in the air, so take everything with a grain of salt, but we are still feasible for launch somewhere around the 2030 time horizon. As always with mission development, expect the timeline to shift to the right, not to the left. So what's the evidence that's needed? So I kind of want to bring this back to the review paper and Mike's presentation. And I know a lot of people on the line here aren't directly involved in the mission, but the point I want to make is that the snow community has made such drastic strides forward over the past decade that it really allows us to move the mission forward. And it's steps that people may not think are directly related to KU band remote sensing of snow mass, but there's a lot that's gone on in the snow community. I put these scatter plots up here not because I want to talk about the retrieval itself. We have the outlines of a functional system, we think, but to show that these are the types of scatter plots that the space agencies want to see, right? They focus on things like this. Show us that the retrieval works. Give us a convincing case that you can take the data from this mission and produce useful products from it. I completely understand the logic of that. We need to do this in a more convincing way than we have to date, and we're continuing to work on this. But I just wanted to show that, we have retrieval systems, we can produce plots, but we need to beef up evidence like this to convince agencies to make the level of investment that's needed in a mission of this sort. So this is kind of the end result. And I think, of course, people don't appreciate fully the amount of work that goes into all the underlying work beneath this, which I want to talk about next. So I just wanted to acknowledge the really community-wide, the snow science community-wide contributions that have made a mission like TSMM possible to get even where it has. And of course, we're building greatly on the legacy of Core H2O. So a lot of work was done during phase A of Core H2O. that we're borrowing from, learning from, and building on. And so we have experimental radar measurements, tower-based in Finland, tower-based in Switzerland, tower-based in the US. We have airborne data from multiple different sources, like the SWISAR, for instance. So we have multiple assets that we're pulling together that are providing, really useful experimental data. I think we're still overall kind of data poor at KU band. We don't have as much airborne data as we'd like, and we'll try to improve on that in future winters. But really, the snow community has done a tremendous job in improving and increasing the amount of radar data we have at our disposal. Field measurements of snow physical properties. So when I was doing passive microwave work 2 decades ago, we're looking at snow grains on a pit card. Even up to a decade ago, that's what we were doing. Now everything is quantitative, everything is objective. So we have the ice cube, we have the SMP shown in those top photos. We have so much knowledge that's been gained from micro CT measurements. And then what I'm not really talking about on this slide, but we could talk about, of course, is how this improved measurement of snow microstructure has fed into improved radar modeling. So there's communities across the US and Canada and elsewhere that have really pushed forward our ability to model radar backscatter response to snow. And it's that modeling piece that is really an important part of the retrieval side as well. And then there's the modeling, this physical snow modeling piece, which is on the right here. And I'm just showing an example from the Environment Canada system on the right, snow grain size and SSA field. We can now, with increasing quality, produce, fields of snow microstructure, snow density profiles. They're not always perfect. There's a lot of problems on the snow modeling side as well, but it's this synergy between the remote sensing, the modeling, and the measurement improvements that have been made over the past decade that we're really building the mission on. So again, I just really want to emphasize that the snow community has really made huge strides forward that have allowed the mission to be positioned the way it has. So one thing I want to mention here is that I think a unified vision has emerged for how we can extract snow mass information from spaceborne microwave observations. And microwave could be passive microwave, it could be radar. But when we look at existing products like the Snow CCI, passive microwave derived sweep product, they all sort of borrow or use an approach that's kind of generally consistent with what Ghislain Picard and others have published this past year. Ghislain has, this group is not directly involved in TSMM, but it's a great example of how the huge strides that have been made by groups like this to advance our understanding of grain size influences, how we treat that from a modeling and measurement point of view. The SMRT package that we have now to handle the radio transfer piece of this. We have this unified vision, I think, for microwave remote sensing of snow that involves modeling, that involves remote sensing, obviously, and that is built on improved physical understanding from field campaigns. And so I think one of the things we often hear in the snow community is that in soil moisture, for instance, decades ago, they identified L-band as the key for them. And that was emissions. They were successful in pushing L-band missions forward, both from ESA and from NASA. The snow community has always struggled to say we have one solution. And that's because snow is so dynamic and different depending on where you are that there isn't one solution. But what is emerging is these frameworks for analysis that regardless of the actual measurement you make, we understand the value and the approaches to how we combine microwave measurements and snow models to get towards the end result that we all want. So maybe we don't have a single technology that we can all identify as the one solution, but I think we have these unifying frameworks now that are coming forward that we can build on. And the review paper that Mike talked about, I think does a good job of capturing a lot of those. This is what the analysis flow chart looks like for TSMM. I won't go into too many details, but there's 3 really important components. There's the physical snow modeling part. So we at Environment Canada run Crocus as the snow model embedded within SVS2. SVS2 is the land surface model kind of writ large. Crocus is the snow piece of that. From Crocus, we can force it with meteorology from our forecast system, and it provides all the initial conditions that we need, including microstructure. So these, again, are not perfect, but they don't need to be. It's really, really helpful, though, and essential, actually, that we have this physical snow modeling component. Without this component, we don't really have a mission. And so the outputs from the snow modeling system are really important for two different reasons. Number one, we know we can't derive SWE everywhere all the time from spaceborne radar. When the snowpack's wet, if the forest vegetation is very, very dense, we want to bring in either from other remote sensing methods or from the model, and then have a merged SWE product that is multi-source. So the modeled SWE is going to be a key component of that. We also know for both the snow water equivalent retrieval piece, as well as the radiance-based assimilation piece, which is in the blue box here, we need microstructure to help with that part as well. So the microstructure, the snow modeling part really informs both step number 2, which is the retrieval of SWE, the direct estimates of SWE from the mission data, as well as the blue box here, which is the backscatter assimilation within CalDAS. CalDAS is the Canadian Land Data Assimilation System. What we've shown in previous years is that assimilating radiance assimilation of L-band data from SMOS and SMAP has really improved the treatment of soil moisture in CalDAS or within CalDAS. And the hope here is that assimilation of KU-band radar backscatter will do the same thing for snow mass. Now we know this is not a trivial thing. And so I'm over simplifying or perhaps being very glass half full in how this will happen. But these are the steps. We know what the important pieces are. Now we have to just finish the hard work to get the mechanics set up, start to do all the tests, and move everything forward. So this is the sort of general concept we have for how the data will flow within the mission. Sujay Kumar and his group, as well as many snow-related people, recently have a paper out on sort of land data assimilation perspectives looking forward. And I really love this figure that they use. I've photoshopped a few little elements around with it here, but the background figure with the black text, this is from Sujay's paper, and then the red text is just all the pieces of the science implementation that we're thinking about for TSMM. So there's a land surface modeling component, so we know we have to develop that. We have to develop CalDAS on the data assimilation piece. There's retrieval algorithm development work that's based on, smart use of radiative transfer modeling. We have the EO component, which comes at this point just from airborne and tower-based data. We know we're going to have to do CalVal once we have the mission up and running. And then in the middle here, where all the hands come together, will be the simulator. So this is the piece a year from now when we have the simulator piece that will help us bring all of these elements together. And so hopefully what people realize is that, the snow community, not just the snow remote sensing, but the snow modeling community, the data assimilation community, all of these pieces are super important. There's a lot of work to do to advance all of them. And we want to use tools like the simulator to bring all these pieces together. So I'm getting down to the end of what I wanted to say today. So these are just sort of some summarizing thoughts. I think within the snow community, the science justification for a mission focused on seasonal snow has always been strong. I don't think in any of the mission review processes that I've been part of or I've heard about from others, I don't think we've ever received feedback that snow isn't important or that snow isn't a compelling thing that needs to be focused on. Snow mass is a well-known observing gap, so we have a compelling case. That's the justification piece. The mission readiness piece, that's always the harder part, and that's where where I still see the challenges that lie ahead for us with TSMM and with other mission proposals. It's this piece to be convincing to people who aren't within the snow community that we have things dialed in to the level that investment in a mission is timely. I think the community has made huge strides since Core H2O. I think I've said that many times already, but I think we're at a point on the readiness side now that's better than anywhere we've been in the past. Is it far along enough? I'm not sure, but it's farther along than it's ever been, which is a really great place to build from. From a scientific mission partnerships point of view, there are myriad partnerships going on within TSMM and outside of TSMM that have moved the science forward. Some of these, we have some formal partnerships within our science team and with other international groups like our colleagues in Finland. We have many more informal contributions from people who are doing work on the modeling side, the assimilation side, the fieldwork side that are super helpful. So again, there's just really a lot going on here and the landscape is very active. The fact that there will be a NASA, there will be for sure be mission proposals from the US side, and then hopefully one of them gets selected. So this will change the landscape. I think the main thing is that there's excellent communication between the TSMM team and CSA and our NASA colleagues. Nobody wants to do anything that's duplicative, but we're going to see how we can do complementary things. One recent development in Canada was that the federal government just invested significantly in AOS. That's the Atmospheric Observing System, which is a NASA mission. Canada is contributing hundreds of millions of dollars towards specific instruments that wouldn't be on AOS without that investment. So we have this model now for how perhaps a dual country mission could develop, or we can keep them separate. Lots to talk about, lots to think about there, but the partnership opportunities are pretty interesting. Some mission fundamentals that I wanted to just restate is that we view, well, for Environment Canada to participate in this mission with CSA, it must be fully open data. And that's something that in Canada has been a struggle with past missions. So anyone who's tried to get RadarSat data knows that we do not have a strong heritage in open serving of radar data from missions. That's going to change. Otherwise, Environment Canada can't participate. So I think we're pretty clear that we have a good pathway forward there. We also want to make sure we're facilitating sort of a sense of ownership in the mission beyond just those of us who are directly involved in the day-to-day planning for the mission. So I hope people feel engaged and interested, and I hope sort of my comments today have sort of helped make clear that through open data, through the efforts of the community, we really want to make this, as broad and as open a process as is possible. And then finally, on the mission selection side, there is a bit of a lack of clarity in Canada on how missions are selected. So there's nothing like an ESA Earth Explorer process. There's no decadal survey as in the US. It's much more ad hoc. So the key is to stay in the game, keep agencies investing in mission development, keep the science partners engaged, and then when the opportunity arrives, be in the right place. And I think that's very much what we're trying to do, and very much where we are right now. Also, finally, for the broad interests that are captured on this call, we know that KU band radar won't address all of our challenges. So in particular, in very deep snow, for instance, that might be a challenge. I've already talked about dense forest areas, wet snow. So again, a multi-source, multi-frequency, multi-platform approach, harmonizing remote sensing with modeling, I think that's really the way forward. And just to circle back to Mike's presentation, the review article, again, is so valuable to show the community interest in the mission. UHA recently led a paper that provided all of the SNOSAR data, which was acquired during Core H2O Phase A. So that data is all openly available now and documented in a consistent way. So these sort of community efforts are super valuable and really more fun to do than working on our own anyways. I'm going to finish just by leaving this slide on the screen. This is the outcome of our socioeconomic benefit study in one slide. It's kind of the benefit areas that were identified. In many cases, we have dollar numbers attached to these, which helps sell the mission. But this is what we want to see from a mission like TSMM. We want to see it address monitoring and prediction. We want to see it help in very applied areas like hydropower management. We think there's a climate story here too. So this is sort of the sales slide of what the impacts from the mission are. So I think that's my last slide. So I'll take questions. Sorry if I went a bit long. And also thanks to Mike, because he really set the stage really well with his overview of the review paper process.
That's great, Chris. Thank you so much for the very detailed and very thorough overview. So any questions for Chris? Please just speak up or put anything in the chat should you wish.
I have a technical question.
Hey, Julian.
Yeah.
Yep.
It's with the retrieval on the snow modeling part. You said that the modeling is going to provide snow microstructure, I think from SVS and Crocus. I just wanted to know what type of snow microstructure parameter that you get from the modeling. Yeah,
so all the initial work's been done with SSA as the output. So Crocus does provide, and we're running it in obviously a multi-layer configuration, but we need to be realistic about how many layers we can run in an operational context. But right now we're using SSA, and we're using field measurements of SSA from both the IceCube and the SMP to validate that. And of course, in Arctic snowpacks, for instance, crocus, every snow model struggles getting the layering right. We're doing a little better in non-Arctic snow. Yeah, that's the approach we're taking at this point.
If I could just maybe add a question on the back of that, Chris. You mentioned about using that first guess from the model output, and you also said it doesn't have to be perfect. Have you got a feel for how much tolerance there is, how imperfect first guess can be while still being of real use to the assimilation scheme?
Yeah, I can't give you a direct answer to that. I know you've been part of some work that's sort of attempted to quantify that. So I think what you really need to do is nudge the cost function into the proper space, right? Because we all know that this is sort of an ill-posed retrieval problem because of the microstructure influence. So you have to nudge it towards, is this a fine-grained snowpack? Does this have a large depth hoar layer? Things of that nature. So I think it's more of a nudging process than a exact fixing process. That's probably an unsatisfyingly vague answer, but it's one of the many questions that I hope we can answer really well once we have a tool like the simulator in place. It's a question that's a bit elusive at this point.
Any other questions out there for Chris? Got one more kind of lined up, and you teed it up again about the simulator. Can you tell us kind of what the process is for the creation of that, or where I know elements of that will be replicated elsewhere? Could you just give a little bit more information about basically the hands that came together in the diagram in the middle, and say where that is and how that's progressing?
Yeah, so this is sort of a standard, having a mission simulator is kind of a standard step in the mission development process. Typically, you don't develop a simulator until phase A. So this is another example of how we wanted to we can't wait to phase A because of the way CSA kind of makes their decisions. So we want to do it as soon as possible, and we convinced CSA of the importance of that. So they're providing the funding for it. So there's different components to what you essentially want is to generate synthetic scenes of data. So you need to set up the parameters of the radar, its performance, the geometry of each scene. But most importantly, you need to have information on the state of the land surface. So what we're going to do is couple the scene generation part of the simulator with the Environment Canada prediction system. So it'll kind of mimic what you would get in operational context. So all the snow information, the ancillary land cover, topography, soil moisture, all that information will feed into the scene simulator from the prediction system, and then synthetic KU Bansar data will be the end result. So we're just starting to engage on this with our industrial partners, exactly how this will look. It's a complex thing. We know what the Core H2O simulator looked like, so we have that as a model, which is super helpful. Yeah, so that's kind of the plan. So yeah, stay tuned.
Cool. Okay, Mike, please go ahead.
Yeah, thanks for showing all that, Chris. It's so exciting and so cool to see all those different pieces come together. And well, while you were talking, I was just thinking about how each of those comments you made, one after another, all represents like their own little world, their own little piece of a puzzle of one of these missions. So it's just really fun to see all that come together. And thanks for stressing the value of that review paper and kind of supporting the whole thing. I didn't mean to sound pessimistic earlier. More that I've been kind of down in the weeds for a while. So yeah, I guess my question though was, I think we both were kind of reaching for this kind of reality that progress in this space has resulted from many progresses. All of these different things, including that paper by Ghislain, which I loved, and think it could be potentially super important. And I was sad we weren't able to include it in our review because it came out after. I guess when you start thinking about stitching everything together, the fact that there's so many different progresses, it almost makes it harder to adequately build algorithms, and it takes a lot of people and a lot of time. So like, do you have any ideas or thoughts or brainstorms about how to jumpstart or speed up or fastify these efforts?
Yeah,
I know I'm stuck there.
Yeah, and we're still stuck too in the, or maybe not stuck, but we are comfortably in a place where we haven't specified exactly what. So I spoke in generalities a lot today, right? I have a lot of flow charts. I have a lot of sort of general language. Specifics, we're still working on very much, and we haven't settled on any specific pathway forward as far as implementation goes. I think we know how we want to do it. We don't know the specifics of that. And I think part of that, we're very challenged from a capacity point of view. So we don't have a lot of science capacity to advance the mission. We're doing the best we can with the scientists we have and with our university colleagues. That's one of the things where having an open source simulator will, I hope, you know, in a coordinated and organized way, greatly increase the number of people who are working, you know, on this sort of thing. So we have to make a lot of decisions still on how exactly to do this. And I think we couldn't, for instance, write an ATBD. So an ATBD is an algorithm theoretical basis document. We need to have that at some point. We don't need to have it at this point. So I always keep saying we're not even in phase A yet, right? So we're still early on in the mission. And, you know, I'm not sure if anybody from CSA will ever watch the recording of this. I don't think there is anybody on the call. So I'll speak very freely and just say it's pretty challenging to have the full mission implementation decision be taken before phase A. I don't know why they want to do that, because all the things that you normally do in a phase A is have a mission simulator, right? You know, really you want to convince people at the end of phase A, okay, now give me the X million dollars I need to build and launch this thing. I guess it's good that we can maybe get that done sooner, but it just does concern me that we're compressing a lot of important science into the pre-phase A period. So, and it may mean that we end up in this period a long time, because the last thing I want to see is rush forward, move into phase A successfully. Hey, that's great, but we're not actually prepared. That's when we would get exposed as a community, you know, as not being ready, and we don't want that. So I'd rather be slow and I won't use the word slow. I would rather be methodical in how we step through this. I would rather be very collaborative and seek partnerships with other countries and agencies if the right thing lines up to do it right, than to rush forward just to say we got something approved, because then you run the risk of looking stupid afterwards, and nobody wants that. So that was a very long, meandering answer to your excellent question. Thanks.
Thanks, Chris. Go ahead, Ed.
Yeah, hi everybody. Can you hear me okay?
Sure.
Yeah, I want to just add my kudos to both Chris and Mike for great presentations and efforts and summaries, and sort of sitting back and taking it all in. They're both noted, and many of the folks who've participated in that, since Core H2O, there's been a lot of pieces of the puzzle that have been produced by different groups within the community, and things like snow missions, serve as catalysts to really focus those, efforts, those individual efforts. And but it seems like, and I think Chris just mentioned it also, it would be great if there were a mechanism, or maybe better mechanisms for individual groups. Maybe there's a group that's focused more on field measurement techniques, and maybe at a different place there's a group that's more focused on EM theory or snowpack modeling. It's sometimes very hard for, if you're in one of those stovepipes, to know what's going on in the other stovepipes. So maybe there's a role for SINTER there to help lower the barriers, just by, like if you were a student or a professor at a university working in one of those areas, how would you even know what's going on and who's, in some other area, and who's doing it? The thing that both Mike and Chris mentioned about how much advancement there's been done since the time frame of Core H2O about a decade or so ago. Easily, I think, we've all heard of person years. I think there's easily one or two, or maybe even more person centuries of work that's gotten us to where we are today versus, the Core H2O time frame. And if we could somehow coordinate that, better, I think that would help all of the mission concepts. And even if, in the worst case scenario, if none of them get selected, it would help us get ready for the next opportunity.
Yeah, just a few comments on the coordination piece, because Ed's right, it's super important. And there's, you know, I sat in on a SnowX Zoom call yesterday where there were presentations made on SnowX science, and you know, the number of young scientists, early career researchers working in the snow community, it's changed a lot over the past decade. It's much more dynamic than it was both in Canada, in the US, and Europe. I think there's a lot going on, which is great to see, but we do need to stay coordinated as best we can. I know, like Marie Dumont has her Ivory project, which is really pushing forward the snow, you know, CT measurements, the modeling, go to a completely new framework. And so the community needs, you know, to stay informed on all these things. How do we do it? I mean, it's been a challenging few years. I think for those of us who are at the seasonal snow meeting in Davos a couple of months ago, the IGS meeting, it was great to see everybody out again. And I think I learned more in those few days than I did from, you know, all the virtual conferences in the years before. So we have our work cut out to stay coordinated, but it's a really important thing. And even just knowing who the right people are to talk to each other, not just in the science field, but at the programmatic level. So who at CSA should be talking to who at NASA? Who at CSA should be talking to who at ESA? What's the right level? When do you have these conversations? How do you facilitate those connections? There's no clear process for this. There's no guidebook. So you have to just sort of try to figure it out and do it as collaboratively as possible.
That's great. Yeah, I think just to answer one of your answer something you said there, Ed, is that one of the roles for SINTER is to provide platforms like this, virtual platforms for dissemination of up-to-date information and also dissemination of linkages and how things work. Very rarely do we all work in a bubble. We have to work productively to work together. So I think there's capacity for us here to be able to advance that in terms of just, yeah, the sharing of knowledge and the understanding of where we are right now. Not necessarily the championing of one thing or another. I think that would be a dangerous precedent set. Moreover, I think just the capacity for people to link together is going to be critical. Sorry, go ahead, Ed. Go ahead.
Oh, just a quick suggestion. I mean, Chris showed that that diagram that you know, that he I think got from Sujay. You know, that lists a number of different areas. I don't remember what all of them are, but I don't know if this is possible, but you know, like even on a SINTER website, to just have lists of different groups who are working on these different areas. You know, how many of us actually know who all is working on, you know, any one of these areas? Oh, maybe it wasn't this one. I was thinking of something else. Yeah, sorry. You know, like the electromagnetic modeling, the snowpack modeling, the field measurement techniques, you know, field campaigns in general, right? If one group's planning a field campaign, if others know about it and they've been, you know, they themselves are not field campaign people, but they, you know, maybe they're snowpack modeling people, and they think, wow, you know, if we only had this kind of measurement from the field, that would really help us out. But you know, they don't even know who to talk to.
Mm-hmm.
Well, we have a partial solution. Certainly, thanks for suggesting that. So I'll put in the link. It's in the chat a link to one of the pages on the NSIDC webpage under SINTER umbrella, which is just groups that do snow research. And so if you followed that link I've just put in, you'll notice a variety of different groups, of different institutions, of different data products. And we're very keen, as always, to host anything that's there. Ideally something with a degree of permanency, but not necessarily. So I put a call out in the summer for people to, you know, self-promote their own groupings, and hopefully that might be one small way of having a one-stop shop for places where people can find out globally where people are interested in snow-related research. So hopefully we can do something towards that. And yeah, maybe any ideas are always welcome about how we can develop and how we can try and increase the positive impact on people's research. We're kind of coming to almost the top of the talking point now. So is there any last questions from anyone?
I have one last one.
Go for it.
Hi, Chris. Really nice presentation. I just had a question on, like, you showed or you had the slide about the scatter plots and showing that, like, we need to see these retrievals work, and that sort of powerful data visualization for people who, you know, approve these proposals and all that. I'm just wondering, like, what do you think the areas or sort of some of the weaknesses are that people or researchers should push towards, whether it be from airborne retrievals or different snow climates, different depths, different types of vegetation, that are sort of some of these gaps that people can start filling to help sort of bolster and, you know, make the argument for this technology more robust as all the different satellite proposals go forward?
Yeah, that's a great question, Jack. Thanks. I think so that the holy grail would be to take the STURM snow classification, and for each of the climate classes, have a convincing scatter plot that shows with this approach we get a SWE that has skill, you know, to some certain standard metric, and that we know that each climate class of snow has its own challenges, and so one solution may not be able to do that for all of those. And so number one, we should be honest about that, right? We should be honest about what the limitations of each technique are. But to specifically answer your question, if we could, you know, and you probably could start now to piece together, okay, C-band cross-pole and really deep snow shows some potential, right? There's definitely something going on there. We have KU band, which we think we have some convincing results for sort of boreal and subarctic snow. So it's just really piecing all those things together. I know, like some of the work you're doing on the L-band side, there's really multi-frequency potential, and I think understanding what the strengths and weaknesses of each of the approaches are. So KU band, the strength will not be deep mountain snow, but C-band cross-pole, deep mountain snow. Some of the INSAR, L-band INSAR, deep mountain snow. It looks pretty good. So I think it's how we can start to piece some of these things together and then clearly show, maybe using a modeling framework, how it all comes together. So again, I'm speaking very generally.
Yeah.
We need to start making specific decisions on how to actually implement some of these things, but you know, we'll get there hopefully soon.
Yeah, I think that the STURM node is really interesting too, because you could even look at like one radar scene, or, you know, one line, it might have different snow classes within that, and look at performance and use that as a, you know, the baseline to talk about a broader area. So yeah, that's really, thank you for those thoughts. Appreciate it.
Yeah, thanks.
That's great. Okay, with that, I think we should draw this to a close. Just a couple of quick things. Firstly, if you're interested in becoming part of the SINTER kind of executive committee, we've got an election coming up. Please self-nominate, send a message to sinter@nsidc.org. We can take it from there. It's really grateful to both Chris and Mike for talking through the review paper and where that's leading us with TSMM. And mostly as well, thanks to everyone on the call who's been listening. Please spread the word about what we're doing. We'll have another seminar probably early on in 2023, and we'll be in contact through the SINTER list. We try and be judicious with the use of the email. We try and send things when it matters, so we'll continue to do so. But thanks very much to everyone who's been there today, and a special thanks to Chris and Mike again. Cheers, everyone. Have a good weekend.
Thanks. Thanks, everyone.
Happy weekend, everyone.
Thank you.